In this video, we will be covering the concept of the moment gradient effect on lateral torsional buckling. By the end of this video, you should be able to assess the effect of moment gradient on lateral torsional buckling, compare the effect of two different load cases on lateral torsional buckling, and summarize the lateral torsional buckling modification factor equation. Let's take two different load cases. Beam A and beam B are exactly the same beam. However, in case A, the beam resists a single point load. In case B, the beam resists 2 point loads equally spaced along the beam. Assuming lateral torsional buckling controls, would A and B have the same moment capacity? Why or why not? The moment capacity is different depending on how the beam is loaded. Your intuition might say that the capacity is independent of the load case, because in many structural problems, you find a capacity and then you check to see if the required moment ever reaches that value. But this is not the case with lateral torsional buckling, because it also depends on how the moment is distributed along the beam. In other words, if there are large moments across the entire length of the beam, then the section will buckle at a lower moment. So do you think load case A or B would give a greater moment capacity? Seen here is the moment capacity from elastic lateral torsional buckling failure. This portion of the equation is based on a beam with a constant internal moment, as shown below the equation. Of course, we do not always have a constant internal moment. To get the moment capacity for other load cases, AISC simply multiplies the equation by this modification factor. This factor is greater than 1 if the moment varies along the unbraced span. For example, for a single point load in the center, the factor is equal to 1.32. This means the beam will require a little bit greater moment in order for it to buckle. Notice how the moment diagram is not uniform, but is linearly changing so that the maximum moment occurs only at a single point. This is the cause of the capacity increase. Let's take a look at the AISC specifications to determine how to calculate the CB factor. If you flip open to Chapter F on page 16.1-46, you'll see an equation for this factor in the middle of the page. The equation is fairly straightforward. The Mmax value is the greatest moment along the unbraced span. The Ma value is the internal moment measured at 1/4 of the span. The Mv value is measured halfway along the span. And Mc is measured at the 3/4 point. Also note that these are the absolute values of these moments. So even if it is a negative moment, you will plug it into the equation as a positive. An example of where these values come from can be seen with this moment diagram shown for an off-center single point load. Now that we've discussed how to determine the modification factor, do you think load case A or B would give a greater moment capacity? Here are the moment diagrams for each load case. As you can see, load case B has a portion with uniform moment. This is why it has a factor closer to 1. Therefore, load case A results in a greater moment capacity.